Hello students, today we have to study the time period of a satellite. That is the time taken by satellite to complete one round around the earth. On your screen we have earth and the orbit around which the orbit in which this satellite completes the path around the earth. We have r, that is radius of the earth, h, the height at which the satellite is placed above the earth, and the small r, that is the radius from the center of the earth to the point where the satellite is placed in an orbit. So satellite is moving with an orbital velocity, that is v naught. Now we have to find the time period of a satellite. In kinematics we know we have a formula for the time period. We know that time period is given by distance by speed. It is the ratio of distance and speed. Now if we say a satellite is moving with the speed v naught and the distance which the satellite travels, that is the circumference, and the circumference is given by 2 pi r. This way we can calculate the time period. So the time period will be given by distance, that is the circumference, and the speed, that is v naught. Now, since we know that v naught, that is the orbital velocity of satellite, which we calculated in the previous lecture, we know that orbital velocity v naught, that is given by root of g me divided by r, where g is the gravitational constant, m is the mass of the earth, and r is the radius of curvature, or you can see radius from the center of the earth. If we square both the two, we'll get v naught square is equal to g me divided by r. Now we will substitute this v naught square in the time period equation. So here in time period we are squaring all the terms since we have to substitute v naught square. So we will get the time period square as 4 pi square r square divided by v naught square. And in place of v naught square we will substitute it with g me divided by r. Or we can say we can replace the time period square by 4, that is equal to 4 pi square g me into r cube. Now if you see 4, that is a constant, and pi square in this equation, it is again a constant. G, gravitational constant, that is a constant. Me, mass of earth, it's also a constant. Now you can see T and R. T and R both are in the numerator, so the two have a direct kind of relationship with each other. So we can say that for any planet or star, here we are considering the earth, square of time period is proportional to the cube of distance from the center of earth. So if you increase the term R, there will be an increase in the term T. So what we mean by here, if you place the satellites higher from the center of the earth, from the surface of the earth, the time period will also increase. If you decrease the term r, time period will also decrease. That means if you place the satellites closer to the earth, time period will also decrease. What does that mean? The time taken by the satellite to orbit around the earth will also decrease. Now we have to next find the height at which you will place the satellite in an orbit around the earth. For that we have again t square is equal to 4 pi square divided by g me. Here we are replacing the r, that is small r, with r plus h. Since we know that r is equal to r plus h, we can take this term on one side since we have to find the height. So cross multiplying the two, we get r plus h cube is equal to t squared g me divided by 4 pi square. So we'll take the cube root on both sides. This may find some complicated equation taking the cube roots etc., but we have to do it this way only. Next here what we find, we are doing the cube root of the equation on both sides, and there we get the 3 and 3 will go, and we'll get r plus h is equal to t square g me divided by 4 square cube root. and since we have to find the h, we'll take r on the other side, and that will be minus here. You see here both h and t are in the numerator, which means more is the height, more is the time period. So more time the satellite will take to orbit around the earth. So if we want time to increase, that is the period of the satellite should increase, we must increase its height. Since we know that we have different orbits in which we place the satellites, we have lower earth orbits, we have medium earth orbits, we have geostationary orbits, and if we want a satellite to complete its path around the earth in a shorter span, we have to decrease the height, but at the same time we have to make sure that satellite should not fall on the earth, so its velocity must also increase. That is the orbital velocity, which we studied in the last case. So if you have to increase the time period of the satellite, you have to increase the height. If you have to decrease the time period of the satellite, that means you want because satellites are placed for different jobs around the earth, if you want the information to come in a shorter period of time, you want the satellite to complete the one path around the earth in a smaller time, so you have to place the satellite closer to the earth. Now you see, if we want the satellite should complete one round around the earth, that means in 24 hours we want the satellite to complete one round around the earth. So in that case, if you go back in this equation, you have to place the values. You have to substitute t by 24 hours. Since we want the time period of the satellite to be 24 hours, we want to see at what height we have to place the satellite if we want the satellite to complete one orbit around the earth in 24 hours. For this case, we have to find the h, but we know t should be 24 hours. So in this equation, you will replace time by 24 hours. G, you know the value of gravitational constant. Me, mass of the earth, the value we know. 4, it is the value there. Pi, we know the value. And r, that is the radius of the earth, we know all the values. So when we substitute t for 24 hours, we get the height as 36,000 kilometers. So whenever a satellite has to complete one orbit around the earth, it should be placed at a height of 3600 kilometers. Now if you want to place the satellite closer to the earth, that means we have to neglect h in the equation. You see the equation of the satellite, time period, sorry, this is the time period equation. In this equation there was r plus h. Here it was r plus h. But since we are placing the satellites closer to the earth, that means h can be neglected compared to the radius of the earth, because h will be very less. Now if you substitute for different values, for pi square, g, gravitational constant, we know the value. Me, mass of the earth, we know the value. R, that is the radius of the earth. So when we substitute it, we can replace r square divided by gme by small g, that is acceleration constant, or you can substitute the values as they are. Then we find that the time period is 84 minutes. So when you are placing the satellites closer to the earth, the time period also decreases. So they complete the orbit around the earth, one round around the earth, in just 1.5 hours approximately. So if I have to find the information, get the information from different parts of the earth in a shorter time period, we'll place the satellites closer to the earth. But at the same time, we know the satellites will move with a very high speed so that they don't fall on the earth, because the two forces have to be balanced. And this way we have in practically different satellites. We have the satellites in low earth orbit, that is the orbits closer to the earth. We have the satellites in the medium earth orbits, and we have the satellites in the geostationary orbit, where the satellite completes one round around the earth in 24 hours. So this was about the time period and the height of the satellite. Thank you.